Lesson 8.4 Determining Wave Speed Part 2 Factors influencing speed. The speed of a wave is determined by the medium, not the frequency. In gases, higher temperatures increase wave speed because faster molecules transfer energy more quickly. In solids, speed is higher in more rigid materials. For waves on a string, the speed depends on the tension, where tighter strings are faster, and the linear density, where thicker, heavier strings are slower. Lesson 8.4 Determining Wave Speed Part 1 The universal wave equation. The speed of a wave can be calculated using the universal wave equation, V equals F times lambda. Because frequency and period are related, speed can also be expressed as V equals lambda divided by the period. This equation is universal because it applies to all waves, whether they are water ripples, sound waves, or light. If you know any two variables, such as speed, frequency, or wavelength, you can solve for the third. Lesson 8.3 Wave Characteristics 1 Geometric features. Waves are measured by their physical shape. Amplitude is the maximum displacement from the equilibrium point, measured in meters for transverse waves, or pressure for longitudinal. Wavelength $LAMBDA is the distance between two identical points, such as crest to crest. Phase describes a specific point's position, and a phase shift occurs when one wave is displaced relative to another along the x-axis. Lesson 8.2 Types of Mechanical Waves Part 2 Sound and complex wave. Sound is a longitudinal wave that requires a medium to travel. It cannot exist in a vacuum. While sound travels as longitudinal waves in fluids, it can travel as both transverse and longitudinal in solids. Many natural waves are complex, combining both motion, such as water waves where molecules move in an oval path, or seismic waves from an earthquake. Lesson 8.2 Types of Mechanical Waves Part 1 Transverse versus longitudinal. Mechanical waves are classified by the direction particles move relative to the energy flow. In transverse waves, particles vibrate perpendicular to the energy, like a plucked guitar string or a water wave. In longitudinal waves, particles vibrate parallel to the energy flow, creating regions of high pressure called compressions and low pressure called rarefactions. Lesson 8.2 Types of Mechanical Waves Part 1 Transverse versus longitudinal. Mechanical waves are classified by the direction particles move relative to the energy flow. In transverse waves, particles vibrate perpendicular to the energy, like a plucked guitar string or a water wave. In longitudinal waves, particles vibrate parallel to the energy flow, creating regions of high pressure called compressions and low pressure called rarefactions. Lesson 8.1 Vibrations Part 2 Media and energy transfer. Vibrations require a medium, solid, liquid, or gas to travel. The efficiency of energy transfer depends on the material's composition. Rigid materials, like steel, have strong intermolecular forces that allow vibrations to travel faster and farther. In contrast, less rigid materials, such as a pillow, absorb and disperse energy, causing the vibration to lose strength quickly.
Lesson 8.5 Properties of Sound Waves Part 2 Speed and Intensity. The speed of sound in air increases with temperature. V equals 331.4 plus 0.606 T. Sound is also characterized by intensity, loudness, measured on the decibel, dB, scale. This scale is logarithmic. For every 10 dB increase, the sound intensity increases by a factor of 10. Long-term exposure to sounds above 85 to 90 dB can lead to permanent hearing loss. Lesson 8.5 Properties of Sound Waves. Part 1 Frequency and Ultrasound. Human hearing generally ranges from 20 Hz to 20 kHz. Sounds below this are infrasonic, while those above are ultrasonic. Ultrasound has many practical applications, particularly in medicine, because it reflects off different tissues, creating echoes. It is used to image fetuses, detect tumors, and even break up kidney stones safely. Nine point three Beats. Summary 1. Creating acoustical beats. An acoustical beat is a periodic change in sound intensity, loudness, that occurs when two sound waves with nearly identical frequencies interfere. As these waves travel together, they continually drift in and out of phase. When they are in phase, constructive interference makes the sound louder. When they are out of phase, destructive interference makes it softer. This rhythmic wobble between soft and loud is what we hear as a beat. Nine point three Beats. Damping and energy loss. Damping is the gradual reduction in a wave's amplitude over time, caused by the absorption of energy by the medium or by destructive interference. For instance, a child on a swing will eventually stop moving because friction and air resistance remove energy from the system. On a graph, damping is visible as a waveform that slowly shrinks in height while maintaining its frequency, eventually returning to a state of equilibrium. 9.3 Beats. The power of resonance. Every object has a resonant frequency, the frequency at which it vibrates most easily. Resonance occurs when an external force or wave matches this natural frequency, causing a dramatic increase in amplitude as energy is added efficiently. A classic example is pushing a swing at just the right moment to make it go higher. While resonance is useful for musical instruments, it must be avoided in building construction to prevent structural damage from large vibrations. 9.5 The Doppler effect. Summary 1. Frequency shifts in motion. The Doppler effect is the change in the observed frequency of a wave when the source and the observer are moving relative to each other. When a sound source, like a siren, approaches an observer, the sound waves are compressed, leading to a shorter wavelength and a higher perceived pitch. As the source moves away, the waves spread out, increase in wavelength, causing the observer to hear a lower frequency than what was originally emitted. 9.5 The Doppler effect. Conditions for the Doppler effect. For the Doppler effect to be noticeable, the source must be moving at a speed that is a significant fraction of the speed of sound, typically at least 10%. Additionally, there must be a component of the source's velocity moving toward or away from the detector. A source moving in a perfect circle around an observer would not produce a Doppler shift. This effect is commonly experienced with emergency vehicles and is also used by police radar to measure car speeds.